Welcome to the Physical World of Motion Part 2. In this section, we're going to cover Newton's laws, gravity, force, weight, projectile motion, and orbital motion. Sounds like a lot, but most of it's pretty straightforward. The SI units we're going to be encountering, the units for mass are the kilogram. So if you want to know the unit for mass in English units, the ones that most of you are familiar with, you're not going to be familiar with the unit for mass in English units, because that is and that is the stone, and 1 kilogram is 0.1575 stone. The standard international unit for force is the Newton, and the pound is actually a unit of force. So 1 Newton is 0.2248 pounds, or 1 pound is 4.45 newtons. You're accustomed to converting pounds to kilograms. That skips a step. And that skips a step because the kilograms being mass, to get to force, you need the acceleration of gravity. So 1 kilogram is 9.8 newtons. So you can see here, since 1 kilo is 9.8 newtons, 1 pound is 2-ish kilograms, right? So weight is your mass times the acceleration of gravity. And we'll have some problems on that. You have to think about that in different ways. Newton's laws. So Newton in the 1600s began formulating what we think of as classical physics and calculus. He had to have calculus to do physics, so he invented calculus. You're very welcome, all your mathematicians. So, law number 1, an object in motion will remain in motion unless acted on by an outside force, and an object at rest will remain at rest unless acted upon by an outside force. Number 2, the acceleration of object is the net force on the object divided by its mass, which we normally write as the force equals the mass times the acceleration. Number 3, for every action there is an equal and opposite reaction. This may also be worded as for every force there's an equal and opposite force. We'll get into that more in some of the discussion. Gravity is vertical motion near a planet, moon, gravity in terms of vertical motion near a planet, moon, or other large body. So this is like your ordinary everyday life gravity. And the variables involved are, we use y for your height above the ground, right? Vertical displacement. Y naught for how high did you start off when you started at time 0. These units are meters, of course. Your velocity vertically and up and down is meters per second. Your initial velocity at time 0 is v naught y. The acceleration of gravity is g. Now, I didn't put a number here because we could have a problem that's on another planet or on a moon or around a star, although we're not going to be on a star where we use this. The equations for vertical motion are y equals minus 1/2 gt squared plus v naught y plus y naught, right? And what does this say? This says your height above the ground is minus 1/2 the acceleration of gravity times time squared plus your initial vertical velocity times time plus your initial position above the ground. In the next equation, your velocity, vertical velocity, is minus the acceleration of gravity times time, plus whatever your initial velocity at time just t equal to 0 was. Apologize for my email kicking off. G is a constant in this, and I'm going to correct this real quick. G is 9.8 meters per second squared. That's the value we're going to be using. In the delta, it's actually a little bit less than that. It's not constant over the surface of the Earth. And the reason it's a little bit less than that in the delta is because we do not have lots of rock here and iron. Rock and iron are more dense, of course, than the gumbo we have in the delta. And rock and iron increase your local gravitational constant. Force and weight, right? Weight is a force, and the variables involved in all this, we use F for force, the units are newtons. F is the force on an object. We use M for mass, that's in kilograms. We use A for acceleration, that's meters per second squared. We use W for weight, but it's also a force, so its units are newtons. And G is what we use for the acceleration of gravity, and you can see that's just an acceleration, meters per second squared. From Newton's second law, force equals mass times acceleration. In terms of gravity, this translates into your weight is your mass times the acceleration of gravity. All right. One distinction between weight and mass. So my mass is about 80 kilos. You move me to the moon. My mass is still 80 kilos. My weight, however, all right, my weight is about 800 newtons on Earth, but you take me to the moon and it's about 200 newtons. Right? And the difference between weight and mass is really simple. I'm fat on the Earth, I'm fat on the moon, but I weigh a lot less on the moon. Projectile motion. Now this looks really complicated, but you've actually seen almost all of this already, right? Projectile motion, we've got your vertical displacement, your initial vertical displacement, your vertical velocity, your initial vertical velocity, the acceleration of gravity, your horizontal displacement, your initial horizontal displacement, and your initial horizontal velocity. There's not an acceleration term in the horizontal direction in these equations for projectile motion because once you throw an object, after it leaves your hand, there's no longer any acceleration horizontally. All the acceleration is vertically. We have D, we use for the range of a projectile. We have theta, which is the angle you fire a projectile off. And we have V naught, which is the initial velocity of a projectile. So what does this mean in terms of the equations? All right. So when you throw a projectile and you shoot it off at some angle, it actually goes in a parabola and lands on the other side, or lands downrange somewhere, right? That initial angle is theta. You've got initial velocity v naught y, you've got initial velocity v naught x, and you have this range d, right? That gets you to all the variables involved here. So in terms of the equations, this is familiar, that is familiar, g is a constant, and once again, I need to correct that to 9.8. Horizontal motion, you're familiar with that equation. That's just horizontal motion with acceleration set to 0. The range of a projectile, d is v naught squared over g sine 2 theta. V naught x in terms of v naught, v naught is this piece, right? V naught x is that piece, and V naught y is that piece, right? Another way to think of V naught x and V naught y is V naught x is the horizontal leg of a triangle. V naught y is the vertical leg of a triangle. And V naught is a very squiggly hypotenuse, right? V naught's the hypotenuse. And so that explains all of these variables. You'll be using these equations. Go ahead and fix this real quick. Orbital velocity, escape velocity, and gravitational bodies. So we have some new variables we're introducing and some constants. The orbital velocity we call v orb. It's meters escape per second, right? V escape is escape velocity, v est. G, capital G, is a universal gravitational constant. And I could even put its value here because it is a constant. Mass of the Earth, we use the symbol m sub e. Mass of the Sun, we use the symbol m with this circle with a dot in the middle of it as the mass of the Sun. R is the distance you are from the center of a planet, and m is your gravitational mass. How does this work in terms of equations? Orbital velocity is the velocity of a satellite going around the Earth or the Moon or the Sun, whatever, right? You could actually use this to calculate the orbital velocity of the Earth. It's g times the mass of whatever you're orbiting divided by how far from the center of what you're orbiting you are, and you take the square root. Now, notice what's not here. The mass of the satellite is not here because the mass of the satellite, it turns out, does not matter. And this is a good thing because that means no matter what the mass of a satellite is, if we stick it out at the same orbit, those satellites will be going around the Earth at the same velocity. We don't have to worry about them running into each other. Um, escape velocity. Escape velocity is the velocity you need to completely get away from a planet and out of its gravitational influence. All right, this is the velocity that will send you off into infinity. And it is very similar to orbital velocity, but there's this 2 in here. So 2gm over r, take the square root. Gravitational force between two planets or two rocks or your pen and the cup on your desk, all right, is capital G, mass of one object times the mass of the other object, divided by the distance from center to center squared. R is the distance from center to center. And that's it for Physical World Motion Part 2. Hopefully you'll get into the discussion and you'll get into the problems, and all this will make a lot of sense. I'll talk to you later.